Welcome back. And in today's discussion, we'll be looking at Chapter 7 and focus on capacity and facilities as part of our discussion of operations management topics. And in this lecture, we'll be focusing on capacity planning. We'll look at basic layouts, and then we'll focus on designing process layouts, focus also on service layouts, and at the very end, look at product layouts and certain hybrid layouts. So that's the agenda for this lecture. Capacity is basically the maximum capability to produce of a company. How much product can be produced in a given amount of time by a machine, or how much information, how much units of product can be stored in a warehouse. All those will be examples of capacity. Capacity planning establishes overall level of productive resources for a firm. What is the level of capacity? How much should be the size of the warehouse? What should be the production capacity of the machines? How many machines should we have? So there are basic strategies for timing the capacity expansion, and three basic strategies in this case. Whether they are that is stay ahead of the needed capacity, so you always have more excess capacity, or you lag behind, that is you always have slightly less capacity than needed in case of uncertainty of future demand, or then third one is average it out. So in terms of from a figure perspective, capacity lead strategy means that you always have extra capacity. So at this point where your actual demand reached the existing capacity, you go out and buy more capacity. And then at that capacity, slowly and slowly your demand keeps increasing, and the capacity buffer becomes less and less all the way till as soon as it reaches your demand equals to the existing capacity. That's when you go out, invest more in another machine or another warehouse, whatever the capacity means in terms of certain resource, and then slowly and slowly let the demand catch up, and then you go out and invest in additional capacity. So that's a capacity lead strategy. Capacity lag strategy is exactly opposite, where you let the demand prove itself. The demand will continue to increase, and that's where the customers are starting to get uncomfortable, or you are over allocated, and that's where you just go out, but you're not sure about what the demand is for the future till the demand proves itself that the demand continues to increase. That's when you invest in the capacity, but you only go to the point where it just matches the capacity, and then slowly the demand will outstrip the capacity to a point where you go and make an additional investment to match that existing capacity. So you are trying to always stay behind that. So in this case, the third example is average capacity. So whenever first you let the demand outstrip your capacity, and at this point you invest in the capacity. So you invested in the capacity and you are ahead of the demand, but you let the demand match it and then even outstrip the capacity until you reach this point, and that's when you invest in additional capacity, and then from having lesser than needed capacity, then you reach to jump to the point of having more than, so that's averaging it out. And then final is you can lead it, so incremental expansion, which is going and investing in few capacity units at a time, to a one-step expansion, just buying in bulk when you really are pretty certain about the demand environment. So capacity increases depend on volume and certainty of anticipated demand, as I mentioned earlier. It also is related to strategic objectives and cost of expansion and operations that you have. Best operating level is typically companies try to figure out is at what is the best level at which companies should look into, and that is a percentage of capacity utilization that minimizes unit cost. Capacity cushion is the percentage of capacity held in reserve for unexpected occurrences. It's like a rainy day fund. That is, some unexpected demand shows up and you can't afford to have customers not be able to satisfied in that scenario. So that's where you may have to keep certain capacity as a capacity cushion, not use that just in case something unexpected happens or a breakdown of machines occur. Economies of scale, that is, there is a certain point at which you are producing at best operating level, and that's where you're achieving economies of scale. The more you produce, the cheaper it becomes to produce on a per unit basis, as it's mentioned in many cases. Unit cost decreases as the output volume increases, so fixed costs can be spread over a larger number of units. So if you think of a buffet in a restaurant, which has a lunch buffet, once they make the buffet, even if an additional person comes in, the per unit cost of feeding that one additional customer is marginal. It's a lot less. So the fixed cost of offering that buffet is spread over one more person, and that's where the overall cost of providing that food reduces. So quantity. So in this case, production and operating costs do not increase linearly with the output levels. Quantity discounts are available for material purchases when you buy in bulk, and operating efficiencies increases as the workers gain experience. So those are all economies of scale issues. So in this case, when number of rooms in a hotel, how many should that be? Well, that depends on the average cost per person. So if you offer 250 rooms, and in this case, the cost will either a certain fixed cost of having the room, with, having the hotel of 250 room size. In that case, you still have to provide the concierge service or pool or parking lot or the building itself, security, all those things. But that is being spread over a 250 room hotel. But the same thing, if it's done on a 500 room hotel, the fixed cost will not increase substantially. The parking lot may still be able to, has to be increased slightly, but not as much, whereas the security computers that you have could easily suffice. So things, as a result, the best operating level, you can see the average cost per person will keep on declining, but to a certain point. After a certain time, if you keep on adding the number of rooms, you'll notice that customers will start complaining if they're not getting good service, and that's where the diseconomies of scale will start coming in. So in that case, maybe one has to find what is the best operating level for a certain capacity and customer service level. Objectives of facility layout is to minimize material handling costs, utilize the space efficiently, utilize labor efficiently, eliminate bottlenecks, that is constraining points which actually are reducing the amount of output that you have from the capacity, pressure points, if you will, facilitate communication and interaction, reduce manufacturing cycle time, reduce customer service time, and eliminate wasted or redundant movements in this case. So layouts can have several objectives along these lines. In this case, also, other additional objectives are facilitate entry, exit, and placement of material, product, and people, so as to offer a way to quickly exchange the product back and forth. So think about a sushi boat house where you can easily take product, any empty plates can be easily removed, and fresh plates of fresh sushi can be added without too much effort on a server's part. Incorporate safety and security measures. So some facility layouts are set up in a way that it facilitates keeping the place secure. Promote product and service quality in many cases. Encourage proper maintenance activities, and then provide visual control of activities. Some layouts allow for that. and provide flexibility to adapt to changing conditions, or in some cases to increase capacity as needed. So there are basic type of layouts. So you have process layouts, which is grouping similar activities together according to a process or function they perform. So think of a hospital. All the X-ray machines are all in one area. Surgery, operating rooms are in another area. Pharmacy, pharmaceutical drugs are in pharmacy area. Rehabilitation center, physical therapy area is in one area. So again, you can think of maternity ward is in a separate area. So those are example of process layout, whereas product layout is everything revolves around the product, which is all the machines are set up in a way so as to get the raw materials assembled into a product in the quickest amount of time. And then finally, the fixed position layout, when you're thinking of creating a spacecraft or the new airplane or a ship, the product stays in one place and the various processes come and go as needed. Okay? So in this particular case, you have a process layout in a department store where you can think of in a women's store, you can have women lingerie in one area, shoes in a totally different area, houseware, third area, women dresses, women sportswear. All those are separate areas. So depending on what a customer is intending to purchase or browse through, they'll have to go through different parts of that store before they purchase or exit. And so depending on whether it's a Macy's or Neiman Marcus or Nordstrom's, you can think of each customer will have a completely different movement throughout the store in this case. Same way, you think of two different products may go through production shop floor in a different way. If the lathe department is all in one area, milling department is another area, drilling is another area, grinding, painting, assembly, all different areas, shipping and receiving. So here, after coming from receiving, a product in the blue arrow is going through lathe to another lathe to milling, then to drilling, then another drill operation, then grinding, painting, assembly, and then shipping. Whereas the blue product is going through 3 lathe operations. So they may just go to the first available lathe and then move out to drilling, and then drilling directly to, milling to drilling, and then directly to grinding, back to milling, back to drilling, back to painting, and then assembly. So you can notice that each product is going in a unique fashion. Whereas contrast that to a product layout where every single product that is being produced in this assembly line is going through every single station that is outlined here from in and out. So think of a school cafeteria where every student is going through that predefined route all the way from picking up the tray, going through various stations. Even if they want to buy something or not, they just walk through that area, pick up what they want, and finally go to the cash registers payoff. So that's a product layout example in this case. Comparison of product and process layout. You can see product has a sequential arrangement of activities, whereas this is functional grouping of activities. This typically works well for continuous mass production, mainly assembly line operations, whereas this is for job shop batch production, mainly fabrication. Over here, the product is standardized, make to stock, whereas this is made to order, varied type of product. Demand is stable, in this case in product environment, whereas this fluctuates in process environment. Volume is high in product, low in processes. Equipment are special purpose and general purpose in process environment. Then you move on to workers and product environment. They just monitor the equipment, so the limited skills will work fine, whereas in process, you need to have varied skills, higher skill sets needed. Inventory is low in process, high in finished goods, and over here in process, you have high in-process inventory, low finished good inventory. Storage space is small, whereas over here it is large in process. Material handling, fixed path or conveyor that you use. Over here it's variable path, forklifts are used to create a customized handling of material as needed. Narrow aisles, because there is hardly any worker movement needed. Over here, there are wide aisles for workers to bring, or forklifts to move the items all throughout the workspace. Scheduling is focus on balancing the workstations, and over here is dynamic scheduling as needed, as rolling with the punches, if you will. We use layout, line balancing, product line balancing in product layout, whereas machine location is the key focus on process. Over here, the goal is to equalize work at each station so that the efficiencies are maintained. But here, minimize material handling cost, flexibility becomes a key issue in process layout. The fixed position layout, typical for project, one-of-a-kind product, and fragile, bulky, heavy items are produced here, mostly handicraft or huge items which can't be moved in terms of ships or planes, if you will. Equipment worker and material brought to site, low equipment utilization, high skilled labor. Think of creating a high-rise building. So that's an example of fixed position layout. Typical low fixed cost, often highly variable cost associated with that. So let's look at designing process layouts. And in this case, goal is to minimize material handling cost. And there are several approaches to that. One is called the block diagramming approach, where we minimize non-adjacent loads and use when quantitative data is available. So when we exactly know how much is the transaction volume between one department and another department, that's where block diagramming can be used. Relationship diagramming is used when quantitative data is not available, but you only have the location preferences available in that case. Okay? And now let's go to block diagramming and look at that. In this case, unit load is looked at, quantity in which material is normally moved. Non-adjacent load is distance farther than the next block. So non-adjacent means one department is adjacent to another department. So department A is next to department B and then department C. So any load that is transactions between department A and C which are not adjacent to each other, in that case that is considered as a non-adjacent load. So steps are to create load summary chart, how much is the transactions between one department and another department, and calculate two-way movement, how much transactions happen back and forth, and develop trial layouts, minimizing the number of non-adjacent layouts. Because what you want to do is reduce the amount of load that is traveling in the distance. So we want to make sure that composite number is the least amount. So here is an example of a particular layout that exists in a building. We have currently department 1, 2, 3 are all in one line. So you can see department 1 and 3 are non-adjacent. So department 1 and 5 also non-adjacent because you have to go through either department 4 or department 2. And then 4 and 5 is down there. And in this case, from and to, you can see department 1 to department 2, there is a load of the transactions, the items moved are 100. And in this case, department 1 and then you have department 1 and 3 is 50, whereas department 3 to 1 is 60. So between 1 and 3, you have a total of 50 and 60, which is 110. So in this particular case, you can see that is between department 1 and 3, that's the 110 that is being computed, which is coming from a total of 60 and 50 add together 110. So what we need to do is, so between 2 and 1, this is 0 over here, and 1 to 2 is 100. That's a total of 100. Between 1 and 3 is 50 plus 60, and this is between 4 and 2. 2 and 4 is 50. So this will be added to this. That's 150. And then this is 5 and 3. 3 and 5 is 50. 50 plus 50 is 100. This is just 40, and this is just 60. And those are the numbers that you end up seeing right here. that I just calculated for you. We already discussed how this part has been calculated earlier. Now, non-adjacent loads are basically the ones indicated by the dotted line. So you can see, you can still cross over from 2 to 4, that's still adjacent, but it's 4 to 3 is far away, and 1 to 3 is far away. So in this particular case, that's a total of 110 plus 40, that's 150 units that you have. Now in this particular case, if you were to move items around, you can notice that by manipulating things around, by moving 4 up there and interchanging 4 and 3, you can see the non-adjacent loads are reduced to 0, because now in this case 1 and 4 has 0 transactions. 1 and 5 has 0 transactions. So basically what you want to do is from here try to see, you need to make sure 1 is further away from 4 and 5 because that's the only one where transactions are 0. So basically by moving 3 over here and moving 4 over here, you end up achieving, so moving 4 over here and 5 over here, you're basically achieving exactly that solution. So over here, everything is right adjacent to each other, and they'll end up improving the productivity. So the block diagramming example in this case would really come up with the initial block diagram that they had was 1, 2, 4, 3, 5, and the final block diagram, you set it in a way that what is the space requirement needed and how it needs to be set up. So it could be done in a way that it allows for adjacent load. Now, in terms of relationship diagramming, the focus is to create a schematic diagram that uses weight lines and denote location preferences. So you indicate various locations, and this the tilted triangle indicates the location preference. That's called the Mother grid that you have, which is format of displaying managerial preference for department location. So here is an example of production offices, stock room, shipping and receiving, locker room, tool room. So in this case, the taxonomy is A is absolutely necessary that they should be adjacent to each other. E is especially important, I is important, O is okay, U is unimportant, X is undesirable. So you don't want those to be together. So for example, you don't want offices right next to the locker rooms. So that's undesirable by the managers. Whereas production, it's okay to have it next to offices, but it's absolutely important that production is next to stock room so that the material can be delivered quickly to the production floor. And it is important that it's close to shipping and receiving, and especially important with the locker room so that the workers can take care of if there is any injury or they need to get after their end of their shift, they can get back, change their clothes, and leave. It's absolutely necessary that production is next to the tool room so that the repair of the machines can occur as necessary. So you get a sense of where things ought to be throughout the company, and based on that, one can easily create. So in this case, diagram with the original layout, you can see A, which is especially important, is indicated by 5 lines. E is 4 lines, I is 3 lines, O is 2 lines. Unimportant is single line, and then wavy line is X, which is absolutely not desirable. So again, you can indicate all those things in that sense. And the revised outline, you notice that we have totally avoided the linkage between offices and locker room. So that is not linked. So we avoid as many we want to really avoid the single line and the wavy lines in this entire process, and that's what we have done. So the only one which is left is offices and tool room in this particular scenario, but that's the best answer that one can get in this case. Now, in terms of computerized layout solutions, you have a variety of computer software that is available. Craft is one, which is computerized relative allocation of facility techniques that can be used to calculate the best layout solution for a particular scenario. Core Lab, which is computer relationship layout planning. Pro Model and Extend offer you visual feedback of how a particular layout will work in a particular place. Allow users to quickly test a variety of scenarios. So it's almost like computer-aided design, CAD. So same way, it is a computer-aided layout that is being created by Pro Model and Extend. 3D modeling and CAD, as I mentioned, now just using a 3D modeling. If anybody were to go to Home Depot and try to work with the Home Depot staff to create revised remodeling their project that they are doing, it can be done on a CAD to visualize what the new kitchen will look like or the new wing in their house will look like. So that's the 3D modeling where layout could be shown exactly to indicate how things will visually work in this case. So available in Wiz Factory and other similar softwares. Now let's move on to designing service layouts. Must be both attractive and functional. Free flow layouts are encouraging browsing, increase impulse purchasing, and are flexible and visually appealing. So there's grid layouts allow for, and in this case, there are different type of store layouts. You have, this is the free flow layout where items are all over the place and people can browse through and then pick up items that they like. So almost like a weekend market, farmer's market type of environment, if you will. And then go back to grid layout, where encourage customers' familiarity. They're familiar with that place. They know when they're buying groceries, there are certain area which always has the milk, and other areas which has produce. Others have canned goods, etc. So they can go in, get the stuff, come out in quicker fashion. So you're able to take care of usual customers in a quick way. Low cost, easy to clean, secure, good for repeat customers type of layout. So this is an example of grid layout that can be provided in an example like Safeway, where people can easily go in and go in a particular aisle if they want to get breakfast cereal versus kitchen towels versus canned goods or produce or soda, etc. So they can just get what they want and move. Then you have the loop and spine layout, which increase customer sightline and exposure to product while encouraging customers to circulate through the entire store. So IKEA has an example of that. Several other stores which make sure that in order to get the items, you have to pretty much go through the entire store. So this is an example. So in a loop, you enter, and then you pretty much have to go through every single area before you can get out. Same thing in spine. The only way you can, if you want to buy something over here, you pretty much have to go through everything. You can bypass something, but still everything is in your visual view in case last minute impulse comes through. But this allows for people to go through and visit the rest of the store as well. And so that's one of the key things that you look at. So in this case, let's focus on the designing the product layout, which is the objective is to balance the assembly line. And in this case, line balancing tries to equalize the amount of work at each workstation. Precedence requirement is physical restrictions on the order in which operations are performed. And cycle time is the maximum amount of time a product is allowed to spend at each workstation. So in this case, let's look at the formulas. So CD is the production time available divided by the desired number of units. So that gives you the cycle time that is designed in this case, and 8 hours times 60 minutes per hour will give you the number of minutes you have available for production, and desired unit of output is basically 120 units. So 480 minutes divided by 120 units give you 4 minutes per unit that you have as the desired cycle time. So in that case, given that cycle time, so what you really want is the cycle time maximum time spent on any station. So you can't have anything more than 4 minutes on each station in order to make sure the product keeps moving, and the final outcome is that cycle time is maximum of time on any one of these workstations, which is maximum of 4, 4, 4, which is 4 minutes. So every 4 minutes a new product is coming out of the production line. But how much time does it take for one particular product to go through this, which is 4 minutes over here, plus 4 minutes over here, plus 4 minutes over here. That's the flow time, total of 12 minutes. So cycle time is the maximum time spent at any station, whereas flow time is time to complete all the stations, to go from start to end. But if you want to look at after how many minutes does one unit gets completed, that's 4 minutes. Every 4 minutes there's a new product coming out. Now efficiency of line and balance delay. So in this case you can calculate the efficiency, which is sum total of all the completion time of elements from I to j, and number of work elements are j. And then in this case actual cycle time for each workstation time, the number of workstations that you have. And minimum number of workstation is basically calculated by summation of all the times divided by the desired cycle time that you have. So balance delay in this case is total idle time of the line, which is n times CA, which is actual cycle time, minus whatever is the time sum of all time completion of all the elements. So in this case, line balancing procedure is draw and label the precedence diagram, calculate desired cycle time required for line, calculate theoretical minimum number of workstations, group elements into workstations recognizing cycle time, precedence constraint, and calculate the efficiency of the line in case we are looking at making sure it is working and how efficient it is and what is the idle time, etc. Determine the theoretical minimum number of workstations and acceptable efficiency level that has been reached. If not, we repeat the step from 4 onwards. So let's look at an example just to illustrate that. And in this case, let's look at line balancing. Here you have 4 different elements. Press out sheet of fruit, if you think of fruit strips that are being created. So that's the first thing that can be done. It takes 0.1 minutes. Cut it into strips, and at the same time, while it's being cut into strips, you can also cut it into various fun shapes. And then both of these can be rolled up and packaged, put together after you brought it. So you can create a whole package which has both fun shapes as well as strips of these fruits. And but D can only be done after B and C is completed. So you can see B takes 0.2 minutes and C takes 0.4 minutes, and then D, the last activity, takes 0.3 minutes. And in this particular case, you can see with this precedence, you have the desired cycle time. You have 40 hours a week times 60 minutes per hour, which gives you 2,400 minutes per week available time. What is the total quantity desired in that of production desired in that week is 6,000 units. So that comes out to be a desired cycle time of 0.4 minutes per unit, which if you think you can easily do it, but let's see if it can actually. So in this case, 0.1 plus 0.2 plus 0.3 plus 0.4, which is total of 1 minute, divided by 0.4, you're looking at 2.5 or 3 workstations. So in order to really do this, it has to be done in a way that you have these 4 activities are being done in 3 workstations. So that's the only way to accomplish this. So in this particular case, you notice that if activity A is done, that takes 0.3 minutes. Remaining elements are B and C, because as soon as A is done, both B and C can be initiated. Now, workstation B, you still have 1 minute left in this. And so activity A is done, which takes only 1 minute. You still have 0.3 minutes remaining in here. So activity B only takes 2.2 minutes. So both A and B can be done in one workstation, and you still have 1.1 minute to spare. And remaining elements are C and D. Now, activity C by itself takes 0.4 minutes. So that has to be done by itself in a one workshop, because that's the maximum cycle time you can't go over. So in this case, if you recall, the precedence diagram is good, but these two are being done by the one worker on one workstation. And C is being done separately, and D, since that's the third workstation you're going to use, and it still has 0.1 minute to spare. Now notice that desired cycle time is 0.4, and number of machines needed is 2.5. In this case, we have 3 machines. That's the nearest round number that you can come up with, which includes 2.5. So you have workstation 1, which has 2 activities being done, A and B, taking a total of 0.3 minutes. Workstation 2 does activity C in 0.4 minutes, and workstation 3 does activity D in 0.3 minutes. So altogether, you can notice you have some total of activities, which is, again, if you go back and look at this formula right here, sum total of all the activities, and that one is 0.1 plus 0.2 plus 0.3 plus 0.4, which is a total of 1, divided by the total time available on 3 workstation, which is 3 times 0.4, which is 1.2. So 83.3% efficient. So in this case, so that's an example of, you can see the remaining time is idle time. So 83% efficiency, so 16.7% is idle time, if you will. Computerized line balancing, it uses heuristics, a rule of thumb, to assign tasks to workstation. Longest operating time can go first, or shortest operating time can go first. Most number of following tasks, that is the activity that can be done first, or least number of following tasks. So you can come up with any rule of thumb that works for you. Rank positional weight, which is priorities given ahead of time. Then you can use a cellular layout, group dissimilar machines into work centers called cells that process families of parts, as I mentioned, creating family of bolts versus families of nut versus family of paper, or various other similar design of products that can be placed together. Processing requirements. So production flow analysis, reorder parts, routing matrices to identify a family of parts with similar processing requirement. Flexible manufacturing system, automated machining, and material handling system, which can produce an enormous variety of items. And mixed mode assembly line processes more than one product model in one line. And in this case, the cellular layout, how this is done is identify families of parts with similar flow path, group machines into cells based on part families, arrange cells so material movement is minimized in this case, locate large shared machines at point of use. So here is an example of part families, or a family of related grocery items, if you will. So for consumers to pick up all at the same place, thereby saving time. So original process layout, you can see could be quite jumbled, items moving all over the place, which when you see it in a matrix, you can see exactly how various parts are related to various machines. They're all over the chart. And this can easily be revised into a cellular layout. You can notice the 3 different products are going through this nicely well-defined cells, if you will. So if you go to Costco, they have a food court where anybody who just wants to buy a pizza or any food item can just have to go to the food court, which is a special cell that they have created. If you go to Walmart, they have the electronics cell in there where anybody can just go buy electronic goods and come back, or they can go get their oil change for an automobile outside, or they can go to the garden center, and that's a separate cell. You can go to Costco and get a 1-hour photo service, or any other store for that matter. So those are all examples of various cells that occur in. So in this case, by looking at these are being determined by moving the routing reordered matrix where A, D, and F are being handled by these machines, and they all can be easily done. Whereas machine 369 can easily take care of CG, and you have this very small instances which have to be taken, addressed separately. But other than that, you have the machines dedicated to various parts very nicely, and routing is done. And that way, one can easily redefine part movement within a cell, and you can say, okay, worker 3 will take care of these 3 machines, whereas worker 2 will take care of these 2 areas plus this area, and then worker 1 will take care of the final assembly plus the start point. So that's a way of cellular layout. Advantages, reduces the material handling and transit time because of predetermined work, division of work. Reduce setup time, reduce work in process inventory as a result, better use of human resources, they know exactly what to do. Easier to control, easier to automate. In terms of disadvantages, inadequate part families will make it harder to easily categorize things into nice areas. Poor balanced cells can also happen. Not everything can be stratified into various categories. Expanded training and scheduling of workers and increased capital investment does require. So you can see advanced manufacturing cells that can be used in this case. And in this case, flexible manufacturing systems are the other type of layouts which can be consist of programmable machine tool, automated tool changing, automated material handling system, which is everything is being automated to produce the product in this case, which takes away the concept layout, but now everything is being done by automation. So combines flexibility with efficiency. Layout differs based on variety of parts and size of parts processed. Average processing time for part completion will also make that determination. So fully implemented FMS, you can see the machine is pretty much going through the entire machines and producing the process. The only thing that worker is doing is monitoring and loading, unloading. And in this case, one can easily look at mixed mode assembly lines, produce multiple models of any order in one assembly line. Line balancing can be done, U-shaped lines, flexible workforce as well as machine model sequencing. You can see examples of U-shaped line balancing that has been provided. And in this case, same precedence diagram, but now you can get a sense of how balancing in a straight line versus balancing in a U-shaped line. So you can look at this as a cell, and rather than in a balancing or straight line where you're only looking at A, B, C, D, and E separately. Okay? So that pretty much wraps up our discussion of Chapter 7 of capabilities, and we'll see you later for a discussion of future topic of operations management. Thank you.